today more than ever, I guess I should record this. Halfway through, what I should do is just stop the recording and then tell you guys like a trade secret and then start the recording again. That would be pretty funny. All right. So, you've got your first test coming up on Tuesday. Don't worry, just 10%, just a little quiz, let's call it. Doesn't matter what you call it. You could call it a midterm if you want, but when it's only 10%. Is it yeah.
So it's just like a...
Yeah, so it'll be just the first 50 minutes of class will be for the test. So it's not even the whole time. It's going to be just 50 minutes. And then we'll do a little lecture after. Okay. So you've got test number 1 on Tuesday next week. Okay. And it will cover up to and including, of course, and including 2.3, which I am hoping I can get through to the squeeze theorem today, but to be honest, it's not looking good. So we might just wrap it up next day. We will start 2.5, which won't be on test 1, it'll be on test 2, right? So it'll be up to and including 2.3. And it'll be test number 1 will be held in the first 50 minutes of class, right? So it's just a little, and then lecture after. Okay. So, hey, thanks for boosting our numbers. And now I can look, span the room, scan the room, maybe span the room. I don't know. All right, so last day, we just kind of started getting into the idea of limits, right? And like I said, if you've dealt with limits before, then this is still kind of review, right? But we looked at finding the equation of a tangent line, right? And so we looked at finding the equation of a tangent line, right? And the tangent line is like the line that touches the curve only at one spot, right? So finding the equation of a tangent line at one point on a function, right? So on a graph, we wanted to find the equation of the tangent line. To do that, the first thing we had to do was figure out what the slope was, right? And to figure out what the slope was, well, we can't just find the slope at one single point, right? And so what we did was we used the secant line to draw the points, so to connect 2 points closer and closer to the point that we're interested in, right? And so what we did, right, was to find the slope of the tangent line, the slope of the tangent line, we made use of the limiting behavior of the secant line. Obviously at the point that we're interested in. Okay. So today we're going to keep going with limits. keep building up these limits. First, we'll kind of look at, well, we can keep just figuring out, okay, well, if I take values close to the point that I'm interested in, right, like we did last day, then we should be able to arrive at some limit. But first thing we want to do is just establish the definition of a limit. Okay? And so it's a little bit long, but we need to have it. So suppose f of x is defined when x is near the number a, when x is near the number a, okay. I'll put in brackets, right? So this means that f of x is defined at all the points near a and around a, right, on some interval that includes a, but not necessarily at a. And that's going to be a kind of a common thing that we deal with. So this means that f is defined on some interval, that contains a, except possibly at a itself. Wait, turn my F into a circle, an ellipse. Okay, so f of x is defined near a, not necessarily at a. Then we write that the limit as x approaches a of f of x equals L, right? And I'll just put in a different color here and say, right, just so you know how to read this thing, the limit of f of x as x approaches a, oops, equals L. Okay. So that's how we write it. If, of course, if we can make the values of f of x arbitrarily close to L, right? So f of x approaches L as x approaches a. So if we can make the values, of f of x arbitrarily close to L, by taking x to be sufficiently close to a, x to be sufficiently close to a. And then I'll add, sorry, no period yet, on either side of a, and we'll dive more into that later today, but on either side of a, but not equal to a, and that's what throws a lot of people off with the limits, is we just want to plug in a, and then that's our limit. But that's only going to be true in very rare situations, right? And so we need to develop these techniques for figuring out what the limits are. So this is all a definition, and can I do a pink box around it? Yes, I guess I can. There. So we're pretty hung up on, okay, well, X doesn't necessarily equal A. So what does that look like if we consider 3 different graphs with basically the same function? So side by side, I'm going to try to draw the same function 3 times. I guess I could have copy pasted, but that would be cheating. So imagine that these are all the same functions, right? All on the XY axis. Then if we've got some A here, then at this point, we're saying that this point must be L, right? As X approaches A on either side, then the output is going to be some value L, and that's our limit. Even if it ends up looking like this. Now, let me see here if I can move this over. Even if there's an open circle at A, right, and the actual value of the function is dropped down, right, because we don't care at what it is at A, right, that's not the limit. The limit of this function as X approaches A, right, is still going to stay on that curve, right? So it doesn't care if there's a gap. So the limit here would still be L. And even if there wasn't something to substitute here, when I'm trying to draw this line, I see my poor drawing skills. Right, let's say that there's just an open, right, a discontinuity, and no replacement dot, right? But the limit here is still going to be L. And so the limit as X approaches A of f of X equals L in all 3 cases. In all 3 cases above. So it doesn't matter what it looks like, right? What we need to remember is that, okay, well, if we're talking about the limit of f of X, then we want to know what the actual curve looks like. So we'll do example. What if we have to guess what the value of, so guess the value of the limit as X approaches 1 of X minus 1 over X squared minus 1. This is going to be one of those situations where, well, if we plug in 1, right, we get 1 minus 1, 0. But then 1 squared minus 1 is also 0, which means we're dividing by 0, which is not allowed, right? And so we need to figure out, okay, well, now we care about what X looks like as it approaches 1, right? And so we use the same method that we used last day, where we pick values close to 1, but not exactly 1, and see how this function behaves. And so notice that X equal to 1 is not in the domain. It's not in the domain. So we consider values close to 1. So if we make a table, first I'm going to start with values that are less than 1, right? But close to 1, things like 0.9, 0.99, 0.99999, 99999, right? And so if x is less than 1, we can start with something like 0.5. That's not very close to 1 at all, and then go to 0.9, and then 0.99, 0.999, and 0.99, and we can just plug these values in. Sorry, 4 nines. And we can evaluate f of x. So f of x for the first one would be something like 0.666. 1, 2, 3, 4, 5, 7, 5 sixes if you're counting. 0.526316, and we can just copy these, it doesn't really matter. But it's just to see what's happening here. So 0.502513, 0.500250, and then 0.500025. Right. So as we get closer and closer to 1, but not 1, right, it looks like it's going to get close to 0.5, right? Because it looks like we're going to increase the number of zeros between the 5 and the 25. But if we do, on the other hand, if we look at x greater than 1, right, and close to 1, we've got f of x on the other end. We can evaluate it. We're looking at 1.5, 1.1, 1.01, 1.001, 1.0001. We're going to see the same behavior, right? And so we're going to have 0.40000, 0.476190, 0.497512. And so these are all going to be on the 0.49 side. 2. 0.499750, 0.499975. Oh, because I think they're renovating the bathroom or something down the hall. Ah, okay. It is really annoying. It's like at the dentist. No, don't associate this room with being at the dentist, please. I shouldn't say that. My husband's a dentist.
It's ironic.
Yeah. So we guess, right, if we had to venture a guess here, then the limit as x approaches 1 of x minus 1 over x squared minus 1, well, if we had to pick one, I would say probably 0.5, right? And we'll see later, right, because like I said last day, I don't like just kind of picking random numbers, because actually sometimes it's not going to work, right? But it's where we start. So we guess that the limit as x approaches 1 of x minus 1 over x squared minus 1 is 0.5. Right? So that's what we guess. Even if we had a new function, well, sort of new, even if we consider some function g of x, which is going to be the same as f of x, or the function that we just dealt with, x minus 1 over x squared minus 1, if x is not equal to 1, right? So now we're saying, okay, well, for all the x's not equal to 1, this is what g of x looks like, and it's going to be just 2 if x is equal to 1. So now we've got this piecewise defined function, and so now right? Bless you. The limit as x approaches 1 of g of x, we would probably want to say 2, right? But it's actually still 0.5, right? Because that 2 is just a dropout hollow point, and then it keeps going with g of x, right? So we're not talking what is g of x at x equals to 1, right? We want to know what's the limit as x approaches 1 of g of x. And so for all the other values, right, except at 1, g of x is x minus 1 over x squared minus 1. And so this is still going to be 0.5, right? And this is the same as the previous limit. So that's going to be important to remember. Okay. Let's get into limits that don't exist, right? And then we'll talk about why they don't exist, right? Because there are limits that just don't exist. And there's a couple of different reasons, but there are limits that do not exist. One example, kind of the simplest example, is the Heaviside function, which we denote by h of t, and it's the simple function that says, well, it's going to be 0 if t is less than 0, and 1 if t is greater than or equal to 0. So what does that look like if we had to draw it out? Well, using a different color here, it's going to be 0 if t is less than 0, not including 0, right? So open circle there. And then it's going to be 1 if t is equal to 0, greater than or equal to 0, so including that 0. Okay. And so this function, I'm pretty sure it's the flick of a switch for an electric current at time equals 0, right? It goes from being off 0 to being on 1. And so very simple function, right? But that's what it would look like. And so the idea here that we're looking at is that the limit as t goes to 0, right, of h of t does not exist, which from here on out, we're going to abbreviate D and E, does not exist. If you say equals D and E, that's fine, but, and sometimes I'll slip up too, but it's more of a statement, right? And so what we're doing, before we had our curves and we kind of met at some point on the curve, right? But here, this curve's down here and this upper curve is up here. And so the limit as x approaches 0 doesn't exist, right? Because they don't approach that same point. And so from here, we're going to start talking about left-hand limits and right-hand limits, right? But let's have a look at another one. So here I'll just explain the limit as t approaches 0 of h of t does not exist since arbitrary values close to t equals 0, yield two different results. another function that we could consider that we're not going to look at too closely quite yet, but if f of x is the sine of pi over x, oops, well, what this function is going to look like, let's see if I can do it. It's going to start kind of big lofty waves, and then as you get closer and closer to 0, right, pi is being divided by something very close to 0, and so it starts doing this kind of oscillating, going crazy around 0. And so what happens is the limit does not exist, because depending on what value of x close to 0 you pick, right, it's going to be a value of 0 or a value close to 1, right, because sine goes between 0 and 1, or sorry, negative 1 and 1, but in this case, right, x, and so it goes between t, and it jumps around, and it'll never settle, right, at x close to 0. And so it's going to look like kind of, sorry, they should be, I don't know, something like that. Yeah. And so what we say is the limit as x goes to 0 of the sine of pi over x does not exist, since the value oscillates faster as x approaches 0. So now let's talk about one-sided limits. I think it's the easiest thing to think about is this Heaviside function, right, where we said, okay, well, because we can't land on one value, right, then the limit doesn't exist. So we can extend that and say, well, in order for the limit to exist, right, then the limit from the left has to be the same as the limit from the right, right? Otherwise, the limit doesn't exist, right, if they're different. And so what we do is we can find the right-hand limit. The right-hand limit is when x goes to a, and then we denote the right-hand side or the positive side with a little subscript or a superscript plus. Subscript, no, superscript. And we can read this as x approaches a, where x is greater than a, right? Or usually, I just say from the right, right? Because if x is greater than a, then x is coming in from approaching a from the right, right? So, or from the right. Same idea with the left-hand limit. The left-hand limit we can show by saying, well, oops, I keep wanting to do -1, but it's just x approaches a from the left, right, with the little superscript negative or minus, and we can say as x approaches a, where x is less than a, right, or from the left. So what we get is this theorem that says, so as a result, we get that, well, the limit as x goes to a of f of x is equal to L, right? That kind of arbitrary limit L, if and only if, which we can abbreviate IFF. Not sure if I've run that one by you guys before. Yeah, IFF. If and only if the limit as x approaches a from the right of f of x is L, and the limit as x approaches a from the left of f of x is also L. So what we do, right, is typically we figure out, well, what's the left-hand limit, what's the right-hand limit? Those limits can exist, right? But if they're not the same, then the overall limit as x approaches a does not exist, right? So usually we have to find the left-hand limit and then find the right-hand limit, and then we look at them. If they're the same, then great, it exists, and it is that value L. So the easiest limits that we can look at is if I just give you a graph of functions, and then you have to look at those and find the limits. So let's start there. I'm at 1, 2, 3, and then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Extend my axes a bit. All right. At x equals 2, we've got an open dot at y equals 1 and an open dot at y equals 3. Okay. Now from here, it doesn't really matter, but what the function looks like, but we'll just draw it like that. And then at x equals 5, we've got a closed dot at y equals 1 and an open dot at y equals 2. And we can connect these open dots and extend the function. Something like this. This function is called g of x. Right. Piecewise defined function, but it doesn't matter. It can be one function. And so if we're concerned with the limit as x approaches 2, right, we can see that there's no limit here, right? The limit doesn't exist. But the reason and how we have to justify it is that, well, the limit as x approaches 2 from the left of g of x, well, that's going to be positive 3, right? Because if I'm coming up on g of x from the left-hand side of x equals 2, right, then I end up at 3. And if I look at the limit as x approaches 2 from the right, well, now I'm on that lower shelf, and I'm just kind of, well, I don't know if I should call it a shelf, but top shelf, bottom shelf. If we're approaching 2 from the right, then we're going to end up at 1. So together, we can see that the limit as x approaches 2 overall of g of x does not exist, right, since they're not equal to each other. Any questions about that? No? All right. let's talk about infinite limits. Infinite limits are limits that don't exist, but we try to explain how they don't exist, right? So there's limits that we just looked at where, nope, just because these two functions, they kind of end at different points, they don't exist that way. But when we've got infinite limits, right, we've got these vertical asymptotes, right? And so these functions, the one we'll look at first, might look like something like this, right? And so they're going to infinity, and that's why they don't exist. And so if we consider the limit as x goes to 0 of 1 over x squared, as a side note, how I want you to think about these things is that 1 over x squared can be thought of as 1 over a small number, right? As x goes to 0 but isn't 0, right? We can't divide by 0. But as x becomes a really, really, really small number, right? Then x squared is also going to be a really, really small number, right? And so 1 over divided by a small number is going to make a really big number, right? And you can kind of feel your way there on your calculator. 1 divided by 0.00001 is going to get you a big number, right? And so here, this is going to be a big number, right? And it's just going to keep increasing as x gets closer and closer and closer to 0. So there's no bound on it. And so we can see it by graphing it. And you can use something like Desmos or whatever you want. But what this is going to look like is something, should be symmetric, but I didn't manage very well. So here, the y-axis is a vertical asymptote. Almost always, and I'm only throwing in that buffer of almost just in case there's special cases, but right, if you've got a value that's not in the domain, right, that's gonna be an asymptote, right? It's gonna be a vertical asymptote. And so here, right, x equals 0 is not in the domain, and so, well, x equals 0 is the y-axis, right? And so that's why we've got this asymptote there. So the question isn't if there's going to be an asymptote there, it's going to be, okay, well, the limit, right, as x approaches that asymptote, what's it going to look like? Because another option is, well, they could be pointing downwards, right? We could have this negative, if we flip this on the x-axis, right, we could have this negative behavior. And so, well, let's just summarize here. So we say that the limit, just going back to the one we were just talking about, as x approaches 0 of 1 over x squared does not exist, oops, does not exist, but we write, and this is important, the limit as x approaches 0 of 1 over x squared equals positive infinity. Infinity is not a number, right? So it doesn't exist, right? Infinity is this idea of going as far as you can possibly go and then further, right? And so we say it equals infinity, but that's just a special way of saying it doesn't exist, right? To differentiate between the different ways that a function can, or the limit of a function cannot exist. And so to describe the fact that as x goes to 0 from the left, right, f of x goes to infinity. And as x goes to 0 from the right, f of x goes to infinity again. So like we said, similarly, the limit as x approaches 0 of -1 over x squared, right? So just a flip. We're going to write is negative infinity, because what it looks like now is, right, it's just been flipped. And so now it's going to negative infinity. What if we have something like, so if we consider the limit as x goes to 0 of just 1 over x, right? Might help to have a look at the graph of 1 over x, but 1 over x is going to look like this, right? So we've got zoop, zoop. So now the left-hand limit would be negative infinity, and the right-hand limit would be positive infinity. Those aren't the same, right? And so now the overall limit as x goes to 0 does not exist, right? The individual limits don't exist, but they don't exist in that special infinity way, right? And so here we can say that while the limit as x approaches 0 from the left of 1 over x, from the left, it's negative infinity. And the limit as x approaches 0 from the right of 1 over x, well, from the right, we're going up towards positive infinity. And because these two are not equal to each other, right, the limit as x approaches 0 overall of 1 over x does not exist. So earlier we said that the overall limit was going to infinity or negative infinity, but that's only because both the left and the right hand limits were both going to negative infinity, or they were both going to positive infinity, right? And so if they're both going, so the behavior is the same, right? The left-hand limit and the right-hand limit have to be the same. As long as they're going in the same infinite direction, then it exists, right? But here, if they're going in opposite directions, then the limit doesn't exist. Okay. Any questions so far? No, more limits. You got it. You got it. The vertical line. So now we're going to talk about these asymptotes. The vertical line at x equals a is called a vertical asymptote of the curve y equals f of x if at least one of the following is true. If at least one of the following statements, oops, one of the following statements is true. If the limit as x approaches a from the left of f of x is equal to infinity or negative infinity, right, to not have to write it out a billion times, or the limit as x approaches a from the right of f of x is infinity or negative infinity, then if either of these are true or both of them are true and they happen to be the same, then the overall limit is that value of infinity, right? But in general, this means that we have a vertical asymptote. Okay. So let's look at this from another kind of angle, right? So as an example, show that f of x equals 2x over x squared minus x minus 2 has vertical asymptotes, at x equals to -1 and x equals 2. Okay. Now I'm going to give you some hints and then let you work on it on your own. So the first thing that we do, right, is, okay, well, if there are vertical asymptotes, what I know is x equals -1 and x equal 2 are probably not in my domain, meaning I should be able to factor out the x squared minus x minus 2 into something like x plus 1 times x minus 2, right? And so we can start there and then start thinking about, well, what happens as x approaches these values, right? So not as x approaches 0 anymore, but as x approaches -1 and +2. Right? If they're vertical asymptotes, right, these limits, so we have to rely on limits, right? So what do the limits look like? And essentially what we want to get down to, is it going to be positive or negative? Okay? So it and see where you get to. But it is different from what we've been doing, so expand your mind. Start this again. Okay. I realized, bless you, I shouldn't have like a blank space in the recording for an unknown amount of time. If you're watching it, like, how long did she not talk for? So the question is not if there are vertical asymptotes. We're going to show that there are vertical asymptotes, meaning that the behavior is going to be towards infinity. We just want to know which direction, right? Positive infinity or negative infinity. And so what we're going to do is, well, the first thing I'm going to do is I'm going to rewrite f of x as 2x over x plus 1 times x minus 2, just to make it obvious that at x equals to -1 and x equals 2, right, these are not in the domain. So I'll start down here. Oops. So at x equal to -1 and x equals 2, right, we divide by 0. But the key thing is that the numerator wouldn't be 0 at x equals -1. Right? The numerator would be -2, and at 2 it would be 4, right? And so we're dealing with these numbers, and we want to think of them as being 1 over some really small number, right? We said results in a big number, right? Big being infinity eventually, right? And so, or actually never, but that's the problem with infinity, right? And so, but the numerator is not 0. So we have something, so we have that same situation of 1 over a small number is a big number. And so for our cutoff points, right, we know we've got kind of gaps at x equals -1 and x equals 2. Another thing that we might forget but is going to be important is that, do we have any x-intercepts, right? Does the function cross the x-axis at any point, right? So if we let the function be 0, right, that's going to happen when x equals 0, right? And so we also note, right, even though it might slip off your radar, right, but that f of x equals 0 at x equals 0, right? So we have one x-intercept. There are no other x-intercepts, right, because there's nothing that I can do to the denominator to yield a 0 value, and so the only x-intercept where it crosses the x-axis, right, is at x equals 0. So what we're going to do, right, is we're not saying that x equals 0 is an asymptote. We're just saying that the values, right, the output values are going to change from being positive to negative. And so what we can do is we can draw some sort of kind of number line here. And we've got, let's start at -1. We've got 0 and we've got 2. I'm not drawing these equal, like proportionately spaced out, because it doesn't really matter. I just want to look at what does the function behave like at these intervals. In fact, I'm going to move my 2 in a little bit because I also want to know what it looks like on the right-hand side of 2. Okay. So we can map this out and we can say, okay, well, I know I have asymptotes at 2. See if I can do that better. There. At -1 and 2, right? I also know that, well, my output is going to go from being positive to negative. I don't know which one, right? But it's going to switch from being positive to negative at x equals 0, right? So what I do is I'm just going to look at the function, and where can I put this? The function as 2x over x plus 1 times x minus 2. And just in general, right, if we're in the same space, right, x being less than -1, right, then 2x is going to be negative, right? And then x plus 1 is going to be negative, and x minus 2 is also going to be negative, right? So I've got a negative over a negative times a negative, which is going to give me a negative value, right? And so that's what tells me that this limit is going to be negative infinity, right? And so here, I'll use the same color. I've got a negative value divided by a negative value divided by negative value gives me a negative value. Which means that I can write the limit as x goes to -1 from the left of f of x is equal to negative infinity, meaning it's going to look something like this. Now we can do the same thing, right? But that's why it's important that we had the x-intercept as well, right? Because the output is going to go from being positive to negative, right? But we can take values between 0 and -1, right? Something like -0.5 as just kind of a test point, and plug in -0.5 into the function and see if we get positive or negative values. We don't need to know the exact values, just whether they would be positive or negative. And so the same idea here, well, 2x, if we just think about -0.5, well, 2 times -0.5 is going to be a negative value. And over -0.5 plus 1, well, that's going to be a positive value. So over a positive times -0.5 minus 2 is going to be a negative value. So over here, right, a negative divided by a positive times a negative is a negative divided by a negative, making a positive. Yikes. Right? But if you break it down to just the signs, right, I like to pick some easy value that's in that interval, but then I just look at the signs, right? Would it be positive? Would it be negative? And so what we can say here is that, well, the limit of f of x as x goes to -1 from the right is going to be positive infinity. So it's going to look something like this, right, going up. Same idea, now we're on the interval between 0 and 2, right? The signs for all of these aren't going to change in that interval, and so we can pick something simple like 1, right? And so we get 2 times 1, that's positive. 1 plus 1 is 2 times 1 minus 2, right? And so we get this, we get a positive divided by a positive times a negative, making a negative value, which we can summarize as the limit as x approaches 2 from the left of f of x is negative infinity. All right. So that's going to look like this. We can also say that, well, the point where it switches from going from negative infinity to positive infinity is at 0, right? And so that's where it's going to cross over and start being, you know, negative to positive. And then lastly here, well, if I pick a value that's greater than 2, right, pick 3, for example, then we would get a positive over a positive over a times a positive, which is just a positive value. And so the limit as x approaches 2 from the right of f of x is infinity. And so it's going to look something like this. So what we can do is we can sketch what the function might look like. And so we've got our x-axis, our y-axis. And if we plop down -1, 1, and 2, we already determined that we would have vertical asymptotes at -1 and 2, right? But now we know what they look like. And so coming up to -1, it's looking like -infinity. Remembering that it crosses the x-axis at x equals 0. And from there, it's going to be positive, something like this. And then it's going to go negative as we get closer. Oh, don't know why I did that. There, closer to 2. And then at 2 from the right-hand side, right, we've got this positive infinite limit. So using limits, right, we're able to determine that yes, there are asymptotes, but also which direction they're going, right? Any questions? Oh. Okay. So then let's get into 2.3. 2.3, I'll start on a new page, is where we start to establish limit laws, right? So like I said, I don't like the wishy-washy, oh, pick limits close to it. But there are situations where not too close, right? And so for the limit laws, then we have some rules that we can follow to calculate these limits. And so calculating limits using limit laws. So we're just going to go through and establish all these laws. But if I had to summarize it, I would say, well, if we've got a combination of functions, we can bring the limit inside, right? And so we just need to establish that for addition, subtraction, multiplication, division, right? But essentially, all the laws say that we're allowed to bring that limit inside. So assume, oops. Assume that the limit, oh, clean this up, we're going to use it a lot. The limit as x approaches a of some f of x is, we'll call it L subscript 1. And also the limit as x approaches a of g of x, so some other function, we'll call it L2, right? Limit 1, limit 2. So assuming that both of these exist, right? And so this means that it exists and it is L1, and L2 exists as well. Let C be a constant. Then our first limit law is going to be, well, the limit, oops. The limit as x approaches a of f of x plus g of x we can rewrite that by bringing the limit inside and saying, well, that's the same as the limit as x approaches a of f of x plus the limit as x approaches a of g of x. But both of those can be replaced. So we can replace them and say, well, that's the same as the L1 plus L2. Right? Because we know the limits of those two individually. Usually we want to work this in reverse, right? If we've got a complex function, then we'll be able to break it up into little functions that we can deal with, right? As long as we're adding them up, and find the individual limits, and then we can add up those limits and it'll be the same thing. The second law is the same, except with subtraction, sorry. The limit as x approaches a of f of x minus g of x, and it behaves the same way, is the limit as x approaches a of f of x minus the limit as x approaches a of g of x. Which again, we can replace by L1 minus L2. The next limit law is how do we deal with constants, right? And so if we've got the limit as x approaches a of c times f of x, we said that we can bring the limit inside, but the limit of a constant is just itself, right? And so what happens is we can rewrite this as c times the limit as x approaches a of f of x, but we know the limit of f of x, and so we get c times L1. Same idea, multiplication. You probably got the structure down, but there we go. Fourth law says that the limit as x approaches a of f of x times g of x is exactly what you think it is. It's going to be the limit as x approaches a of f of x times the limit as x approaches a of g of x. Both of which we can replace and say, well, that's the same as L1 times L2. Same thing goes for division. The limit as x approaches a of f of x divided by g of x is the limit as x approaches a of f of x over the limit as x approaches a of g of x, which, because I've got a page break here, I'm going to keep writing here, is the same as L1 over L2 if L2 is not equal to 0, right? We can't divide by 0 still, so assuming that the limit of g of x is not 0, right, we're allowed to do this. Our sixth law is stemming from the fourth law, which says, well, if I've got f of x to the power of n, well, that's f of x times f of x times f of x times f of x n times, right? I can just bring the limit inside on all of those and say, well, if I've got the limit as x approaches a of f of x to the power of n, that's the same as the limit as x approaches a of f of x all to the power of n, which is going to be L1 to the power of n. Finally, before we get into the special cases, right, the only one that we haven't talked about is the roots, right? If we take the roots of a limit, so if we take the limit as x approaches a of the nth root of f of x, we can rewrite that as we can even sneak the limit just onto the f of x, just because of how the nth root behaves, right? That's the same as the power one that we just talked about, except now it's 1 to the power of 1 over n, but it's going to behave the same way. And so now we can rewrite this as the nth root of the limit as x approaches a of f of x. We need to keep in mind, right? We can't take the even root of a negative number, right? We can for an odd root, right? But if we've got an even root, then the limit as x approaches a of f of x has to be greater than or equal to 0. Right? And so what we say is that if n is even, right, the limit of x going to a of f of x must be greater than or equal to 0. But otherwise, in general, we can rewrite this as the nth root of L1. Right. But again, if n is even, then L1 has to be greater than or equal to 0. Some special cases, both of which are going to be obvious, right? But until we have them on paper, we can't really use them, right? And so 8 says that the limit as x approaches a of a constant is just that constant, right? And so if your function is a constant, so that means that y equals c for all values of x. Well, regardless of what point of x you're approaching, right, you're going to have this constant value. And the 9th law says that the limit as x approaches a of x is going to be a. Because now you're saying, well, y equals x, so they're going to have the same, right? The input is the output. So then if x is approaching a, that means that y is approaching a, and so then the limits are the same. These should get a pink box around them, but this is going to take a while. We wrote a lot, didn't we? Oof. All these limit laws. But most of these, or probably all of these, should feel pretty intuitive, right? As long as you can think, well, I can bring the limit inside, right? As long as that limit doesn't violate math laws, right? Dividing by 0, taking the square root of a negative number, right? Then I'm fine. All right. Let's do an example. What if we have to evaluate the limit as x approaches 2 oops, as x approaches 2 of 2x squared minus 4 over x plus 5. Use those limit laws and bring that limit as close to all the x's as you possibly can, right? You should end up with 4 different limits to work with. I'll set it up here. Okay. So if I start kind of slow and I bring on that limit, because grand scheme of things, right, I've got a fraction, so I'm dividing a function by a function, so I can bring that limit onto the numerator and onto the denominator separately. So the limit as x approaches 2 of 2x squared minus 4 over the limit as x goes to 2 of x plus 5, and I can start there. One thing to keep in mind, right, is that as long as that denominator doesn't equal 0, right? And so I can do this as long as the denominator, does not equal 0, which it doesn't look like it does, right? X plus 5 as x goes to 2. So then, if I focus on the numerator for a little bit, right, if I've got a function minus another function, right, regardless of it being a constant, right, I can put the limit on both of these. So I've got the limit as x approaches 2 of 2x squared minus the limit as x approaches 2 of 4. Doing the same thing in the denominator, I get the limit as x approaches 2 of x plus the limit as x approaches 2 of 5. The only one that's really going to give us grief and not really even is the 2x squared, right? Otherwise, we know the limit as x approaches 2 of 4. Well, 4 has nothing to do with x, so it's just going to stay 4. Same with the 5 in the denominator. And even the limit of x as x approaches 2, well, we know that that's going to be 2, right? And so I'm going to rewrite, right? I can bring that 2 from the 2x squared out front. And so I've got 2 times the limit as x approaches 2 of x squared. But then I'm going to replace the limit of 4 by just 4 divided by the limit of x as x approaches 2 is 2 plus 5. And so I get the limit as x approaches 2 of x squared, right? X squared, we know there's no asymptotes, we know there's no discontinuities, right? And so it feels pretty safe to just plug in 2 as my x, right? And so I get 2 times 2 to the power of 2 minus 4 over 2 plus 5, which puts me at 2 times 4 is 8 minus 4 is 4 over 2 plus 5 is 7. So what this means is that as long as the value that we're taking the limit at, right, so the value of x that we're trying to plug in or find the limit of, if we plug it in and it's in the domain of the function and it's all continuous, right, which we'll talk about later in the next section, but right, if there's no hiccups like dividing by 0 or taking the square root of a negative number, we can just plug in the value, right? And so we say that as a result, if we do not cause a function to be undefined, we do not cause a function to be undefined, then we can say that the limit as x goes to a of f of x is going to be f evaluated at a, right? Because what we could have done earlier in this equation here, if we just plug in x equals 2, there's nothing wrong with that, right? We land on some value, and so we're allowed to do that, right? And as a rule, as long as f of x is a rational function, right? So a polynomial or a polynomial divided by another polynomial, right? And so for rational functions, right, this rule applies. And so what we can say is that if p of x, right, is a polynomial, then the limit as x approaches a, of p of x is p of a. And for actually rational functions, right, not just a polynomial divided by 1, that's a rational function, a polynomial over technically a polynomial, right? Or for rational functions themselves, p of x over q of x, where p of x and q of x are polynomials, then the limit is going to be the limit of, or the limit of p of x over q of x is going to be p of a over q of a. And so the limit as x approaches a of p of x over q of x is going to be p of a over q of a, as long as q of a is not 0, right? So as long as q of a is not equal to 0, right? Still can't divide by 0. Okay. so I guess we could. I'll put a box around just starting here, because that's kind of what we were getting at. So if you've got a polynomial over a polynomial, that's great, right? Because then you know that you can just plug in the values as long as it doesn't cause it to be undefined. If it causes it to be undefined, we usually change the function a little bit, not by changing the meaning of it, just by multiplying by 1 is going to be a trick that we use, right? A convenient one. And so here's a theorem. If f of x equals g of x, for x near a, but not necessarily at x equals a, but not necessarily at x equals a, then the limit as x approaches a of f of x is going to be the limit as x approaches a of g of x, assuming the limit exists. Assuming the limit exists. What does this mean? All it's saying really is that if I've got some f of x that's going to be undefined at a, right, then I can rework f of x, right, abiding by the rules of math, right, and keep f of x the same, just looking different and disguising it as g of x. And then if I'm able to find the limit of g of x, well, that's the same as the limit of f of x, right? And so this is just establishing that, yes, we're allowed to change f of x how it looks, but not what it says, right? And so let's do an example. If I ask you to find the limit as x approaches 1 of x squared minus 1 over x minus 1, that's tricky, right? Because x is approaching 1, but then in the denominator, I've got 1 minus 1, which I don't want, right? Then I'm dividing by 0, and that's illegal. And so, well, what can I do? I can change x squared minus 1 over x minus 1, right? I can factor out the x squared minus 1 to try to get rid of that x minus 1 in the denominator, right? That's often a good choice. And we'll look at some other options that we have, right? And so what we can do is we can say, well, this is actually equal to the limit as x approaches 1 of just rewriting x squared minus 1 as x minus 1 times x plus 1. Right? Those perfect squares over x minus 1. Because I'm multiplying here, I'm allowed to cancel the x minus 1 with the x minus 1. So that's what I mean. We can conveniently get rid of the x minus 1 that's giving us grief. And now the limit as x approaches 1 is just going to be of x plus 1. All of a sudden, I can just plug in x equals 1 in here, and we're all good to go. Okay. The key thing, right, and that's why we need this theorem to say, well, I'm allowed to do that, right? I'm allowed to change the look of f of x, but not the meaning of f of x. Right? And so here, this is going to be 1 plus 1, so the limit is going to be 2. So here, the idea is that, okay, well, x minus 1 as x approaches 1, that was going to be a problem, right? So we looked and we saw, well, what can I do to get rid of that problem? And as long as I'm following the rules of the road, then I'm allowed to do it, right? I'm allowed to change f of x into g of x and then take the limit. And so if limit laws do not apply, right? In this case, if I brought the limit onto the numerator and onto the denominator, right, that limit in the denominator would yield 0, and so the limit law doesn't apply because that was one of the conditions, right, that the limit in the denominator can't be 0. And so if the limit laws do not apply, then we use algebra to cancel out, let's call it the problem. The problem in this case was x minus 1. Sometimes we might have a problem in the square root, right, where the square root, we're taking the square root of a negative number. That's not allowed either. Yeah. Let's consider another example. If we take the limit as t approaches 0 of 3 plus t squared minus 9 over t, and I'll let you guys work on this a little bit on your own. We've got that problem, we can't divide by 0, and so we want to try to get rid of the t in the denominator. And so I'll let you see what you can do. So here we said, right, we can't divide by 0. So the limit as t approaches 0 is a little bit nasty. So we have to get rid of that t. One option that I'm seeing is, well, I could expand the 3t squared. And so I can rewrite this as the limit as t approaches 0 of 3 plus t times 3 plus t, which I'm just going to rewrite as 9 plus 6t plus t squared, and then minus 9 all over t. 9 minus 9 goes away, and so now I've got that common t in the numerator, and so the limit as t approaches 0 of 6t plus t squared over t, I can pull out that common t, and so I've got the limit. And whether you want to cancel from here, or if you want to pull out the common t and then cancel, that's up to you. I'm going to pull it out because I always want to make sure that I have a t that I can cancel. Otherwise, I'm not allowed to cancel that t in the denominator, right? And so that's why I always pull it out, just to make sure that I've got a t to cancel. So t times 6 plus t divided by t, now I'm allowed to cancel it. And so now I've got the limit as t approaches 0 of 6 plus t. All of a sudden, well, that's going to be 6 plus 0. Not going through the motions of taking the limit of 6 is 6, plus the limit of t as t goes to 0 is 0, right? I can just rewrite that as 6 plus 0, which is going to be 6. How about another example? So here we're going to be dealing with the square root, but not really in the way that we think it's going to be illegal, right? But it is going to be our out for avoiding something illegal like dividing by 0. And so the limit as h goes to 0 of the square root of h squared plus 9 minus 3 over h squared. So the h squared, as h goes to 0, I'd be dividing by 0, so that's no good. And so what I'm going to do is, well, I'm going to leverage that the square root of h squared plus 9 and then minus 3, and I'm going to multiply it by the square root of h squared plus 9 plus 3 over the square root of h squared plus 9 plus 3, right? Which is basically multiplying by 1. And so I'm going to rationalize the numerator, sorry. So I can rewrite this as the limit as h goes to 0 of the square root of h squared plus 9 and then minus 3 over h squared. And then I'm going to multiply, and this is what I mean by multiplying by a convenient value of 1. H squared plus 9, that stays the same, but then if we do plus 3, some things are going to cancel, and we're going to get rid of that square root. We are going to end up with a square root in the denominator, h squared plus 9 plus 3, but that's all right. Because hopefully, if we plug in 0 now, right, it's not going to yield a 0 in the denominator. Just as a side note here, what I'm doing is I'm multiplying by, I'll put 1 in air quotes. And how I picked that value is that if I have root a minus b, which I have in the first part, right, in the actual function we're dealing with, times root a plus b, what I end up with is I get a plus root a times b minus root a times b minus b squared. I'm going to get cut off, but so I'm going to be able to know what that number is going to look like approximately. So what I get is I get the limit as h approaches 0 of, well, a in this case is going to be the square root of h squared plus 9, and so I get h squared plus 9, right, no square root anymore, plus, oh, whoops, I didn't need to. The square root of a times b minus the square root of a times b, that's going to go to 0. And so what we're left with, sorry, is a minus b squared. Sorry, a minus b squared. So what I can do, that's why we were using this trick. Felt a little like, hey, it made it harder. But if you had expanded and worked it out, then it would have ended up at a minus b squared. So now we can write, well, h squared plus 9 minus 3 squared minus 9. And then in the denominator, I've got h squared all times the square root of h squared plus 9 plus 3. Plus 9 minus 9 is going to go away. And we can clean this up a little bit and say, well, the limit as h goes to 0 of h squared over h squared times the square root of h squared plus 9 plus 3. Well, these h squareds can cancel, right? Because I'm multiplying in the denominator. That was a combo. Denominator, numerator, denominator. Keep you on your toes. Well, this is the same as the limit as h goes to 0 of 1 over the square root of h squared plus 9 plus 3. The nice part about this is if I plug in h equals 0, right, I'm not dividing by 0 anymore, right? So we made it a little bit nasty, but we got away from dividing by 0. So now we know, right, that essentially we've got a rational function, right, a polynomial over a polynomial. So I'm allowed to plug these in as long as I'm not divided by 0, which is the case now. So now I can just plug in h equals 0 and say, well, this is going to be the same as 1 over the square root of 9. So 0 squared plus 9 plus 3, which, because I've got a page break here, is 1 over 6. Any questions? So like I said, at the beginning of class, you've got your test 1 on Tuesday next week, which is going to be up to and including 2.3. We didn't quite get to the squeeze theorem today, but we'll wrap that up next day. Start chapter 2, or section 2.5, which is not on test 1, it's on test 2. Right, so we'll finish the last little bit of material that we'll need on Thursday, I guess. But for now, I think you've done your bit. So I'll see you guys on Thursday. Bye, guys.